All right, everyone, welcome back to BHI Colloquium. Today we have Lorenz Eberhardt. He's a postdoctoral long-term member at the Institute for Advanced Studies in Princeton. He got his PhD at the ETH in Zurich, and I worked on ADS3 CFT2 correspondence in string theory. And now he's interested in two-dimensional CFTs, 3D gravity, perturbative string theory. And today he's going to talk about partition functions in 3D gravity. Please.
All right, thank you very much. Yeah, as you were saying, I'm mostly string theorist by training, but in my spare time I work on 3D gravity. So today will be just about pure gravity. But if you have any question or you want to discuss anything about string theory or scattering amplitudes or anything like that, you're very welcome. And yeah, I'm here the whole day today, so feel free to. So let me start very broadly. So a large part of our community, I guess it's fair to say, tries to understand quantum gravity at the quantum level, and we are approaching this topic from a variety of different directions. But what precisely does it actually mean to talk about quantum gravity? So for the purposes of this talk, at least, it means that we want to get very quantitative predictions. So we want to be able to give ourselves a well-defined problem and compute what's the answer to it. And in many cases, this boils down to computing some gravitational path integral very precisely. So usually we're giving some boundary condition. So very popular in our community is to have ADS boundary conditions in the context of holography. And then we're trying to compute some gravitational path integral that involves integrating over metrics, summing over different topologies, and so on. And except for very few select special cases, we actually don't know what the rules are. We don't know what kind of geometries we need to include. And so it's very much guesswork. So let me address also string theory. So string theory is one answer to quantum gravity, but it has varieties of features that many find undesirable. So for one, it's somewhat problematic that string theory doesn't really teach us that much about semi-classical gravity, because many questions that involve semi-classical gravity, like black holes and maybe the production of black holes and some high energy collisions and things like that, they involve some very non-perturbative calculations in string theory. And while in principle well-defined, these are just extremely technical and hard to perform. And so that's why string theory hasn't told us too much, in my opinion, about semi-classical gravity. Of course, there are many calculations that have, but in general, it's very hard to do anything like that. So the main reason is because string theory is usually.
What would be the question about semi-classical gravity? You would hope to get the answer to? You could do semi-classical perturbation theory?
Yeah, one question that I find, for example, very interesting is if you take just flat space, Minkowski space, you take some very high energy gravitons, you smash them into each other, and you ask about the production of black holes in that process. That is something that, in principle, involves some very large out states like black holes, but it's very hard to.
That's not strongly coupled quantum gravity. What's semi-classical?
Semi-classical is that we need to sum over different. So that semi-classically, you would perhaps describe this as the formation of some black hole. So you have some kind of photon shell that collapses into a black hole. That's a semi-classical process, but it's very hard to describe something like this that involves a large number of degrees of freedom in string theory. Usually we take the semi-classical process and we perturb around it by putting some little strings or something. And we describe it in that way. But then
we could probably, I guess, so address that problem by starting with well-known exact classical solutions, which describe shells of matter.
Yes.
Collapsing to form black holes.
Exactly.
Perturbative loop computation.
I agree, but that's string theory doesn't tell you to do that. We can do string theory in these kind of backgrounds, in principle, but string theory doesn't tell us that we should consider.
String theory, right? String theory is not especially useful for that.
Exactly. That's the
They
point.
did give us ADS CFT, which I would say is a really good description of many semi-classical processes.
That's true. Yeah. So that's the point of view of the boundary in ADS CFT. So there we know that we need to
Also gave the entropy, which was a kind of semi-classical
Yes, that is one very famous calculation.
I don't understand what you're.
So, for example, string theory. If we don't want to do semi-classical calculation, like say compute the ADS-CFT partition function to some very high accuracy, then we don't know what we need to do. We can take various bulk topologies, compute some one loop approximation around those, and sum over all of those. Perhaps include some geometries with some singularities. We don't know the rules for that. And string theory doesn't really tell us what the rules are, because string theory is not good to tell us things that happen at order 1 over G string squared, non-perturbative 1 over G string squared.
Sorry, if you're including more topologies, that's, I would think that you're doing a non-perturbative.
Yes, that's what because yeah, most of these questions are non-perturbative. I agree.
Right, so how is that semi-classical gravity? If you're including that high genus fraction, how do you think that's true? Classical, not purely.
High genus in the
We're
word.
just talking semantics here. Right?
I think so. Yes.
We're just talking. When
I
I
mean-
hear the word semi-classical, yeah. I think of the classical plus small correction.
I agree with this, but I don't know what this really semi-classical rules even for gravity are, because you can take your favorite solutions that involve some number of singularities maybe and perturb slightly around them. I don't know which ones to take into account and what the precise rules are. That's my whole point. And string theory doesn't really tell you much more than that.
Right.
So it just tells you take different backgrounds, perturb around them, because so there's ADS-CFT, I grant you that definitely. But then there's the question how we interpret the CFT calculations.
But even ADS-CFT interestingly has answered a lot of questions about what kind of non-perturbative topologies we should include.
Yeah,
That's what you're.
So I think all the approaches then that I'm aware of course, there are calculations like the black hole entropy that you and Vafa did that are very impressive in your string theory. And so these kind of calculations exist, but they don't give, at least me, that much intuition. They just say, use some kind of holography and then count the number of states in the CFT. And that is a good answer and it seems to work, but it doesn't really tell me that much what is going on. Yeah, that's roughly what I mean by string theory. Is not, at least I can't see how it's telling me much more of what the semi-classical rules of gravity are.
You mean it doesn't tell you about the bulk. You want to know the bulk answer.
Yeah. All right. Okay, so that's one thing I think we more or less agree on. No? And the other thing is that string theory includes a lot of extra baggage. So you have to include D-branes, you have to include perturbative string excitations, and lots of the stuff that we a priori don't think we would need in gravity. Gravity, we think we just need the graviton and some gravitational waves and black holes, but we don't need all this extra stuff that is around in string theory. String theory has a huge number of massive fields and is vastly bigger than just pure gravity. So if string theory is a UV completion of gravity, that part I think is more or less without doubt, but it's certainly not a very efficient one. It includes many, many additional things that you wouldn't have thought that you need. All right, that's more or less everything I want to say about string theory. Now we go back to usual semi-classic gravity. And maybe I can also clarify here what I mean by semi-classical. So many essentially all the computations that we're doing in gravity, with a few exceptions, are semi-classical. By which I mean that they try to compute usually the Euclidean gravitational path integral by identifying saddles and then perturbing around them. Maybe to one loop order. If you're really brave, you can maybe do a two loop order or something like that. So more or less we're doing computations like this. We're trying to integrate over all the manifolds with some given boundary conditions. So for example, these could be ADS boundary conditions, could be also different boundary conditions. We're trying to integrate over all the metrics on these different topologies, and we're weighing those with e to the minus of the Einstein-Hilbert action. So that's the object we're trying to compute in semi-classical gravity. And we're approximating this by saying it's a sum over all the saddle geometries that we can find or we can think of. And then we're perturbing slightly around these saddle geometries, which is signified by this kind of perturbed gravitational path integral. So that's usually what we do. There are some exceptions, like JT gravity is a notable exception that I will discuss in a second. But you might ask whether this is a good approximation. You might also ask which kind of saddle should qualify as a saddle, because there are, for example, many geometries that have some kind of defects or some other singularities, and it's not clear whether we should include them. And there are even some topologies, and this will be a big part of this talk. There are some topologies that simply don't admit a saddle solution. So this involves the sum of all topologies here on the left-hand side that you can think of. But in some of these topological sectors, there's just no solution to the Einstein equation. And so we don't have this option of just picking a saddle in this class of solution and expanding around. So the question is, do we just throw them out, or what do we do about this? So all of these questions, I think, are kind of very unclear, at least to me. Let me tell you about the theory where essentially all of this has been understood, but it's a very simple toy model. So it's a theory of two-dimensional gravity. By two-dimensional, I mean two space-time dimensions. And it's a theory of almost pure gravity. And this is actually a gravity theory that we know how to quantize. So this is Jaqueff-Teitelbaum gravity. Got to put the reference by Jaqueff and Teitelbaum. But there was lots of activity on this in the last 5 years. And the action is the following. So it's almost like the Einstein-Hilbert action, but there's this additional scalar field phi here that doesn't have a kinetic term. So because of that, it's often called the dilaton, and this is dilaton gravity. And so this theory of quantum gravity is kind of special because there's this phi field, and because of this phi field, you can do the path integral exactly. So you just integrate out phi, and if you integrate out phi, it gives you the constraint that the curvature has to be equal to the cosmological constant. And in two dimension, we understand the possible topologies reasonably well. They're just Riemann surfaces, so you can have any number of genera, and you can compute this path integral exactly. What it essentially gives you in the end is just the volume of the space of Riemann surfaces with negative curvature. So I won't get into the details of this, but you can interpret this also holographically, and there is a dual matrix model. So that's when many works on this in the 90s, and was kind of resurrected and given a new interpretation in this recent work of Sarchenko and Stanford. So let me talk a little bit more about holography. So there's holography in general as a handle on pure gravity with negative cosmological constant. So holography in general, I guess you're all aware, but it says that some gravity theory on some negatively curved space is described by a CFT on the boundary of that space.
Just out of curiosity, has anyone studied the R equals lambda theory in 4D? Any quantum gravity path materials for the
You mean this theory about the D4X here?
Yeah, like a theory where the equation of motion is not rich but scale of flatness. R equals scale of constantness.
Yeah, I don't know, but it would not be easier than studying just regular quantum gravity.
Okay.
So usually the interpretation is that this phi comes from you get this theory from dimension reducing from 3 dimensions. So I guess you can maybe, and this is basically the G phi phi term, like the G of the internal dimension. Yeah, but yeah, so I don't know how useful that is, but maybe someone has studied that. Yeah, so holography predicts that there's some CFT duals to gravity. So we don't know whether there's actually a CFT dual to something like pure gravity. We just have examples, almost all of them involving string theory, where there's some well-defined dual CFT. But many in our community have the hope that there's also something like a CFT dual to just pure gravity. So if there would be something like pure gravity, we would hope that we can capture it in the form of a CFT. So in this Jaqueff-Teitelbaum example, there was actually not a single dual CFT, but there was rather something like an ensemble of CFTs. So there's a question that we should maybe have something like this. There's also lots of recent speculation on this. But in any case, if you have one CFT or perhaps several CFTs that are dual to pure gravity, then these CFTs should have some very special properties. Particularly, they have very few excitations that correspond to graviton excitations. So something like gravitational waves and black holes. So black holes are the other kind of states. And so these are very few excitations if we compare it to CFTs that describe string theory. And recently there was lots of effort in trying to constrain such CFTs and bootstrapping them, meaning that you just impose these consistency conditions that you want these kind of states in your CFT, and you try to see whether such CFTs exist. And there are more and more bounds that constrain these CFTs more tightly. And it's very fair to say that in at least dimension greater or equal than 2, where the notion of CFT is kind of constraining, we don't have a single CFT that even comes close to describing pure gravity. So all the CFTs that we know are extremely far away. So I don't know whether this is a sign or whether we're just failing with that. Yes.
So of course, the loop gravity effort, which goes back to decades, was based on the premise that at first sight we have killing premise that there should be some kind of pure theory of gravity where quality. But another analogy we could draw, of course, is that gravity is a theory with a dimensional coupling constant, and then, like the Fermi theory of weak interactions, that's a strong indication that there's new physics at the scale where the of the order of the metrical parameter, and that there's also some suspicion in string theory that, or not string theory, but quantum gravity in general, that when you can't get away with just one individual, or of them order to satisfy.
That's
so one interpretation that would be that gravity in multi-dimensions just doesn't exist. It just doesn't.
You mean in higher dimensions?
4-dimensional gravity doesn't have any lower dimensional analogs with the same elements. What would you?
Sorry, say again. You would say higher dimensional gravity.
The view I'm leaning to.
Yeah, I mean,
that there is no lower dimensional. That there is nothing below 4 dimensions that outside of anti-de Sitter space that or even including that there's no within an anti-de Sitter space 3-dimensional space you get the whole what I'm just presenting
so
opposite view.
I don't think I presented necessarily a view here, but so I mean, if I understood you correctly, like I totally agree that probably, I mean, there are various scenarios. You could argue for asymptotic safeness, perhaps in 4 dimension, but I guess you argued that there needs to be some higher dimensional operator, like in the Fermi theory.
I'm just saying that there's no evidence against that. There's no evidence against the point of view.
Yes, then I agree with that.
Maloney Whitten is a very strong supporter. Years before Maloney Whitten, there's an even simpler argument, which I think Maloney Whitten boiled down to, is that if you have 2D gravity in 2 dimensions, gravity is quantum field theory. You can quantize it. And there are no signs of anything like a Bekenstein-Hawkins worth of states.
Yeah.
And so there can't be a consistent story of black hole thermodynamics. So we're free to call it's a free world. You could call something a toy model of gravity, but it doesn't.
It doesn't capture the key.
It doesn't capture it, and there were all kinds of a lot of work on 3D gravity. My feeling is 3D gravity, the path integral, and this is also true of 2D JT gravity. It includes space-times with negative metrics. If you put it, so it's not really.
I think this talk will. Gravity. I think this talk will convince you more of your position of this.
Okay.
I do agree with that, but I'm sort of agnostic. I'm also a little bit unhappy that in string theory we have to put in all of this extra stuff, and it's way more complicated. And so it would be nice if there's something like pure gravity, or whether we can make.
It's all this extra stuff, but it's all related by symmetry. It's all unified by the string.
Yeah.
It's all necessary, more importantly.
It's all necessary.
Well, I don't know whether we know that. But,
yeah.
It's necessary in string theory, but we don't know. It would be very nice to see what is necessary just based on some general principles like unitarity and things.
And
like
we
that.
don't know that isn't true.
We have several hints like this,
There are hints of it,
but
yeah.
but making this precise would be extremely important, I think.
Right.
And that would, yeah, I guess, convince a large part of the community that string theory is really the only answer. Okay, so now let me talk about 3D gravity. So after JT gravity, if we go up one dimension, then the simplest theory of gravity that you can probably think of is just pure 3D gravity with a negative cosmological constant. As almost everyone in this field, I'm studying negative cosmological constant because there are things like holography, and it's less confusing. So the action is just the usual Einstein-Hilbert action. And one very nice feature of 3D gravity is that if you try to solve Einstein's equation of motion, then this tells you what the Ricci tensor is. But in 3D, you can express the Riemann tensor through the Ricci tensor. And so this tells you that every solution of the Einstein equation locally looks the same. It's locally always symmetric space. In particular, you can immediately see from that 3D gravity doesn't have any dynamical degrees of freedom. So there are no gravitational waves in this theory. So that's what makes it much easier than 4D gravity. But still, it's very hard, and we'll see that it still has many problems. However, for the purposes of this talk, it's very important to note that it still has black holes in it. That was famously pointed out by PTC. So what is this talk about? I was rambling sort of on general things right now. So in this talk, I want to take a different perspective. And I don't really want to talk about the gravitational path integral, but I want to talk about canonical quantization in gravity. And so this gives access to some other quantities that we don't really know how to compute by the gravitational path integral, but we can access by canonical quantization. And as you will see, there are many infinities in this talk, and many infinities are quite bad, I think, and I don't know how to resolve them. So I think that will more or less point towards what Andrew was saying, that this 3D gravity is maybe even worse than what you would have thought before. And so these infinities, I don't know how to resolve for pure 3D gravity, but there's an even simpler theory of 3D gravity, sometimes called chiral gravity. And in this theory, many of those infinities don't arise. We can discuss that.
Quick question. So
Yes.
in GT, if you do path-integral quantization versus canonical quantization, you actually get two different theories. Is this basically what you're saying here?
So in canonical quantizations, there are various choices you can make. And those choices are basically related to what kind of singularities you allow in the surfaces of quantization. So I don't know. So as long as we're only discussing topologies that don't have these kind of singularities, I think it doesn't matter. But as soon as you start discussing topologies that allow these singularities, then it does matter what kind of quantization scheme you choose. Yes. So, but yeah, you see the kind of non-uniqueness of the gravitational path integral you see coming back here. Okay, so the outline of the talk is now that I will introduce some kind of standard 3D gravity. So this is mostly review 3D gravity. Then we are going on to quantize 3D gravity directly in canonical quantization. And as I told you, there are many kind of bad things going on that I will point out, that many of those are well known, but some are not so well known, I think. And then we go on to this more special theory of chiral gravity, where you can actually solve many things. Okay, so some of these things I already said. So in 3D gravity, 3 dimensions, we can express, and I should say that, so here I'm mostly talking about Euclidean signature. We can express the Riemann tensor through the Ricci tensor. And so if you try to solve Einstein's equation, that in units where lambda is -1 look like this, then they imply that the manifold is locally symmetric space. And being locally symmetric space means that the covering space, the universal cover, is a symmetric space. And so that means that every solution of 3D gravity is just hyperbolic space, which is the 3-dimensional analog of the upper half plane, divided by some discrete group. And so that seemingly is very nice, that we can classify all the solutions of 3D gravity in a very simple way. And as I also already said, the theory is topological. There are no dynamical Bach degrees of freedom, no gravitational waves. But there are still solutions that are black holes. Okay, and the theory is only topological in the bulk. So famously, 3D gravity has boundary dynamical degrees of freedom. And you can see it, for example, very easily if you put 3D gravity on this kind of donut, and the time goes around the donut. This kind of background is called thermal ADS. So global ADS is usually the kind of just where we don't identify the donut here, and it's just a long cylinder. And if we identify it periodically, then we call it thermal ADS. And there is in particular beta around the circle. And so we can try to compute something like thermal partition functions. So in this case, you do have dynamical degrees of freedom, and they are boundary gravitons. So they're gravitons, but they just live at the boundary of the space. And from the point of view of holography, this is kind of obvious, because you expect that there's a 2D CFT, or perhaps a 2D CFT, but at least certain.
But not having gravitational waves doesn't stop you in your tracks.
No, it helps me. It makes my life easier in this case, because I don't have to worry about local questions. I just worry about global questions. Yeah, so in 2D CFT, we have the conformal symmetry algebra, which is called Virasoro algebra. And in particular, the Virasoro algebra implies you that if you have one state, then everything has to fall into representations of this Virasoro algebra. In particular, there are all the descendants, meaning like if you act with the Virasoro algebra, you get many states. They're called descendants, and they correspond to these boundary gravitons. So I think I put the reference here. Yeah, down here. So this was actually discovered way before holography was discovered, and was kind of is often cited as the first indication of holography, and was discovered by Brown and Hill. So in thermal ADS, one can do actually some very nice calculations, and one can compute the gravitational partition functions in this background to all orders in the perturbation series. But this doesn't mean that we understand the non-perturbative question. It just means to all orders in perturbation theory. So this was first done by John B. Maloney and Yin in 2008, and the calculation is more or less what you expect. So if you compute the partition function on this thermal ADS background, what you get is these kind of infinite products. And if you're familiar a little bit with 2D CFTs, these are precisely the descendants that I mentioned before. So these infinite products, you should just read them as harmonic oscillators, and they just account for all the descendants of the vacuum. So this is just the vacuum representation. And here in front, you can read off the energy of the ground state of the vacuum, and it's equal to minus C/12, which is, and from that you can read off the central charge of your potential dual CFT. So the central charge was computed before by Brown and Henno, and it takes this form. So it's 3L over 2G Newton, and L is the characteristic size of the ADS.
So in their calculation of John B. Maloney, they didn't use the Chern-Simons formulation.
They used heat kernel formulation. So they just
all roots.
Yeah, so they computed so the fact that it's one loop exact is not completely obvious, but basically usually spectra are one loop exact. You can argue it from like some conformal block point of view. You don't see it easily from the gravitational path integral. That is one loop exact.
I see.
But it is. But this is not true if you go to some like more complicated backgrounds. Then it's not one loop exact. That's some special feature of this background.
But aren't all the backgrounds just related by SO2Z?
Other backgrounds, I mean, you could consider like handle bodies and things like that.
What if I did BTZ instead of?
Yes, then it's also one loop exact. Okay. So yeah, what I think I didn't include this. Yeah. So what these guys also did, let me just mention, is they summed over all the bulk manifolds they could imagine. This is basically the thermal ADS. So they're given these torus boundary conditions. So the boundary of this thermal ADS is a torus, and you can try to sum over different bulk manifolds with the given torus boundary condition. And the sort of obvious ones are just the modular transformations of this one, which means you flip this around in every possible way, but the boundary is still a torus. But you can, like, for example, here, this is the thermal cycle and this is the spatial cycle, but you could flip them and you get formally a different bulk manifold. So these are the sort of obvious ones you could sum over, and they summed over all of those, and they found various pathologies that I shouldn't maybe get into. But you could imagine including also other bulk manifolds. So there are other papers that claim that these problems partially get resolved if you consider more bulk ones. So I want to go into the direction of quantizing this theory. So I'll now discuss the phase space. So the picture you should have in mind is that there is some spatial size of your 3D gravity theory. So it's a two-dimensional surface, and it's some kind of Riemann surface. So it has some number of poles. That's the genus of the surface. And then this surface evolves into a space-time like that. And I sometimes also later allow sigma to have boundaries. So this would be a 3D manifold without any spatial boundaries. But we could assume, for example, that the sigma is also disk or something. And then this, if we have a disk, then this evolves into a cylinder. And you can ask, what is the phase space if you quantize on sigma? So in the Hamiltonian formulation of general relativity, you can essentially choose the metric freely on sigma. And you can also choose the extrinsic curvature on sigma. But there are some Hamiltonian constraints that constrain these. And basically, if you solve it, so in 3D gravity, you can fully solve these constraints. In the end, you find that the phase space is given by the cotangent space of the space of conformal structures on sigma. So this is actually true in any dimensions, this simple statement. And the space of conformal structures just means the metric up to an overall factor. So you can factor out some function. So in 2D, the space of conformal structures on some Riemann surface, some very famous object, it's the modular space of Riemann surfaces. So you get the very nice statement that the phase space of 3D gravity is just the cotangent space of modular space of Riemann surfaces. So in particular, this M is a finite dimensional space. So its dimension is given by 3G minus 3 plus. So if the manifold is closed, it's finite dimensional, and the dimension is 3D minus 3 complex dimensions, where G is the number of holes. Okay, so now let's go on and quantize it. So quantization is essentially quantum mechanics 101 for a closed surface. It's extremely easy because your phase space is just the cotangent space of something. So that's the standard situation that you have in quantum mechanics. You have some particle or something, then it's described as positions and momenta, and the momenta are the cotangent vectors of positions. So you should think of the cotangent vectors as being momenta. So these could describe the extrinsic curvature of the surface, and the conformal structures as being the positions. And so if you quantize, then the wave function will be simply a vector in this Hilbert space, and the Hilbert space are L2 functions on the modular space of Riemann surfaces. There's a particular measure that I don't want to discuss, but that's what it's fine. But that's slightly going into Netter's question, because this measure depends. So there are various choices for the measure. The kind of most canonical one that you can think of is defined in terms of the Weil-Petersen volume form. But you could discuss other ones, and they would give inequivalent theories. But one important feature here that is maybe slightly surprising, that the Hilbert space is actually infinite dimensional. So I started the talk by telling you that 3D gravity is a topological theory, at least in the bulk, as long as we don't consider boundaries. But here you find that the Hilbert space is actually infinite dimensional. That's not something we're used to in topological theory. Topological theory, we usually have finite dimensional Hilbert spaces. Everything is nice and finite and so on. But here we have a topological theory that actually has an infinite dimension.
Okay. Sorry, but in transcendence theory, if I add a boundary, I also get infinite dimension.
That's right, but here we didn't add a boundary.
Okay, so it's a different issue.
Yes. So this is more as if you would do SI2R transcendence theory, you will also get this kind of issue.
Oh, even on a closed surface in SO2 transcendence, you get
Yeah. Okay. Because the phase space is also non-compact. So this basically boils down the phase space is non-compact. And roughly speaking, every unit volume of the phase space gives you one quantum state.
I see.
And if it's non-compact phase space, you get an infinite dimensional Hilbert space. Okay, so with this, we can already see some very interesting puzzles. So now let's try to compute the gravity partition function on a topology that is a Riemann surface times a circle. So we keep sigma for now to be without boundaries for simplicity. So the Hamiltonian in general relativity is 0. And so if we compute the partition function on such a topology, then we get the trace over the Hilbert space of e to the minus beta h, but h is 0. And so this just computes the dimension of the Hilbert space, which is infinite. So all these partition functions are infinite. So I should mention that when sigma is a sphere or torus, this is sort of a more subtle question, because there are things like mapping class groups and automorphisms of the sphere where you have to be more careful. but at least if this is a genus 2 or higher surface, this is definitely true. And I should mention that sigma times S1 is definitely not of the form H3 mod semigroup. So these are these kind of topologies that don't admit a solution to the Einstein's equations. And so they're sometimes called off-shell geometries. And so this very simple argument already shows you that the partition function on many of these off-shell geometries is just infinite. And I don't know of any natural way of getting a finite number out of that. So there are ways, but I don't think they're very natural. All right. So you might say, maybe that's not so bad, since these are just vacuum bubbles, essentially. There's some closed three-dimensional manifolds. They contribute to the gravitational path integral, but fine, I'll just throw them away because they go into some normalization of the vacuum. I don't care. However, this also happens if you have asymptotic ADS boundaries. So that also happens when sigma has some boundaries. Then it's a little bit harder to see because you have to keep track of these boundary excitations, but you can still repeat the same calculations. And there are basically just 3 exceptions for the sigma where you get a finite answer. For all the other ones, you get an infinite answer. The simplest one is when sigma is a disk. When sigma is a disk, then the topology disk times S1 we already saw. That's thermal ADS. And you can check by this canonical quantization procedure that you get the correct answer. The next simplest one is when sigma is a cylinder. When sigma is a cylinder, then a cylinder times S1, it's just the same thing as a torus times an interval. So that's what we often call something like a Euclidean wormhole. So it's a topology that connects 2 different ADS boundary conditions. In this case, this 2-boundary wormhole partition function was computed sometime 2 years ago by Kotler and Jensen, and this computation recovers. Arguably in a simpler way, I think. And you can also do it for the 3 boundaries. By 3-boundary sphere, I mean that's a wormhole with 3 boundaries. So it's a sphere where you remove 3 disks. So then that you can also compute using this method, and it gives a finite result. And everything else is divergent, just like before.
Are they finite because the Hilbert space is finite dimensional?
Yes, the Hilbert space is kind of even one-dimensional. So let me explain you this, and then I think you'll understand. So the reason why they're finite and the other ones are infinite is that if you draw some topology like this, so this is sigma, it has some asymptotic boundary, but there's some complicated topology here. And now you're trying to describe the Hilbert space here. And then basically there is these bound. So you have to keep track of this beta because there are these boundary gravitons. The fancy way of doing this is to do equivariant quantization. So there's some U1 action on phase space, and you have to basically, your Hilbert space is graded now by this U1. But the point is that there are still many moduli here behind kind of what you might call the horizon. And I'll come back to it in a second. And they lead still to an infinite, to too many infinite directions. So they make, like, even if you fix your charge sector, you still get infinitely many states. And the same happens. So if you have imagine just having 2 boundaries. So you just have this, and there's another trumpet attached to here. So you just have a cylinder like this one. Then there's sort of no moduli behind the horizon. And that's why the Hilbert space per charge sector is at most 1 dimension. And the same happens for 3 trumpets attached to something, because the thing that is behind the horizon is now a 3-punctured sphere. And as you know, the modular space of a 3-punctured sphere is still 1-dimensional. 0-dimensional. So the Hilbert space will be 1-dimensional. But as soon as you have a 4-punctured sphere, then there's a modulus there, and that's why it diverges. Yes.
Yeah, so if this is what I think you're referring to, Kotler and Jensen had a beautiful interpretation of the 2-boundary thing that's computing the fluctuations of the partitions.
Yes.
When you go to the 3-boundary thing, is that the second order fluctuations that now computing the 3rd order?
Yeah, so that will be computing the non-Gaussianities in the theory. So they compute the spectral form factor, right? Basically the two boundary wormhole. But if you go higher, then you're computing the higher moments of the CFT. If you think there's some ensemble of CFTs, then this will compute the 3rd moment. And the 4th moment will diverge.
And is there some check on whether that interprets that?
Not
You can interpret it.
Yeah, I mean, it's even worse because you couldn't even find topology. So these are just very special topologies, right?
Yeah.
But you could imagine there, let's say you take this topology, but instead of this part, you add another part, cylinder part here. Then this would already be a contribution to the two boundary partition function. But there are some moduli here that make it divergent. So what is seemingly higher up in the, what you might call genus expansion or something, just dominates over this other term that they computed. I mean, it's infinite. So there, one problem of 3D gravity is that there's no coupling constant. There's no natural expansion in any kind of topology. If you do 2D gravity, then usually there's an expansion in the number of genera. But in 3D gravity, you don't have something like this. Formally, like this, yeah, I'll mention another. If you try to sum over this genus thing, something else that is very bad starts to happen. But I'll discuss it.
Is there no measure that actually makes the volumes finite for modular spaces?
Well, the Weil-Petersen volumes are finite. So are you asking because I said the phase space is non-compact?
Yeah.
The phase space is not the modular space, but the phase space is the cotangent space of modular space. And so that's a vector bundle, so that's managed, you know.
When you said that the cylinder Hilbert space is finite, are you not counting the boundary galaxy?
No, it's finite, sort of the primary part. So if you're in like a CFT language, if you just restrict to primary states, it will be finite. Yeah, and like on top of that, you would also need to sum over these different, like the sum over this modular images and so on that Kotler and Jensen was doing. But I just discussed like one fixed topology.
Are these three geometries also off shell?
No, these are not really. So the disk is manifestly not off shell because it's thermalious. The cylinder is kind of not off shell because you can pinch the cylinder and then it becomes like two casts that touch each other. So there's an on shell solution, but it's singular. And the same thing happens for the three boundary sphere. And like if you go higher, then I think they're more off shell. But yeah.
So what's the motivation for studying the off shell partition?
Sorry, say that.
What's the motivation to study partition functions in off shell space?
Well, I think the gravitation passing principle says that you should include them. Like we don't have any principle that says only include those topologies that emit this like classical solution.
And is there a way to classify all these shell space times in 3D?
No.
I mean, in organic quantum mechanics, there are all kinds of, contours in a complex way. We could go crazy, including, and I think we understand there pretty systematically that you only include specific context, Euclidean set of functions. And the generalization to that quantum field theory is touchy, and the quantum gravity is even touchier. But we imagine this.
Yeah, maybe. I don't know what the rule is. I mean, would you
But
say
it's not obvious we should include every off-shell configuration.
it's not obvious, but it's also not obvious which one. Yeah, it's not obvious. It's also not obvious which one we should include, which one we shouldn't. I think there's no. I mean, the closest to a potential answer would be string field theory for me, but I won't discuss this here. But so string field theory in principle, I think, gives you a well-defined kind of integral over the string field. And that tells you, but then there's a question how you interpret it semi-classically. But that's the closest where you define a gravity theory by some well-defined path integral, and in principle, you know the contour you need to integrate.
And string field theory famously has many spurious integrals.
Yes.
Complex line for which there is no visibility.
Yes. Yeah.
Spurious poles.
Okay.
Imagine that even if the partition function is infinite on one of these, every single off-shell geometry, their sums could somehow be finite to cancel each other out.
Well, they're all positive infinite things.
They're all
because they're counting the dimension of some Hilbert space. So at least there might be like other, like you could imagine more complicated things, like a circle bundle over Riemann surface. Then it's not obvious that this counts some number of states. That might like give a negative infinity in some way, but then you also have to tell how to regularize all this stuff.
Yeah, it's just that if you want a principle for which off-shell geometries, by looking at the things that you find on answers.
Yeah, right. But they're all, yeah. Anyway, okay.
Why don't you put these on file? What kind of matter we have to add?
That's a good question. I don't know.
Is it would be pathological in some way?
No, because it should modify the stress energy tensor. It's not really the way.
In what way? Can give you, violations of the null energy condition or?
Well, maybe I should also say if you mentioned null energy condition. So I don't know the answer to your question, but if you're thinking about Lorentzian signature. In the
Sure,
Lorentz.
sorry.
So there is definitely Lorentzian solution to this. So you can consider any kind of initial surface and you can propagate it. There's a perfectly well-defined Lorentzian solution. But here there's, yeah, exactly. So it's a Euclidean question. Right. Okay, so
Is it, that's right, you can take any negatively curved two-dimensional Riemann surface and have a turn that into a three-dimensional.
yes, there's even a formula for the metric. It's a very nice, I keep forgetting it, but there's a closed form formula for the 3D metric given these initial conditions.
Zero or negative?
Negative. For positive is much
And
more
there are
complicated.
singularities.
There aren't. No, there can be singularities. So, for example, if you have if you start with the cylinder, that's the two-sided BTZ black hole. But you can always propagate it. I mean, yeah.
You're saying that the Lorentzian propagation will always give you a solution. That will give you some
Yeah.
solution.
Yes. So that's crucial to ensure that this is the correct phase space to check this. If the Lorentzian evolution would give something singular immediately, then this would not be a good phase space. So there are different proposals for the phase space also where people modify something, but then yeah. So it's not completely clear that this is the phase space. You need to check various things. Yeah, you also need. Okay, so yeah, I have nothing very smart to say here, but let me just, I think these affinities are very bad for the gravitational particle. So since they seem to compete with every other computation that we're doing, it's not, I mean, you can say we throw them out. So that's the first option here. We can either throw them out and not worry about them. Or we can also say the 3D gravity perhaps only makes sense as an ensemble of CFTs. And these divergences then mean that all the expectation values that you can potentially compute are all divergent. Such probability distributions exist, but I think then it's also not very useful because then there's no quantity anymore that we can really study that is well defined. We can also say that 3D quantum gravity just makes no sense and we should finally stop discussing it. That's another option. Or the fourth option that I want to maybe discuss a little bit is that we can consider other theories where less bad things happen, but still bad things happen. So let me go to this fourth option. So that's chirogravity. So people mean different things by chirogravity. So let me say what I mean. So in the first order formulation, 3D gravity is described by a dry band and a spin connection. And both of those have one space-time index and one sort of internal index, because the spin connection in 3D gravity, in 3D, you can dualize. Instead of having, usually you have two hypersymmetric indices, but that's the same as one index, 3 dimensions. And you can repackage those into two SL2R gauge fields by just taking these combinations. L again is the ADS length. And then there's a very famous observation that says that Einstein's equation of motion just say that these two gauge fields are flat. And these are the equations of motion of Chern-Simons theory. And that leads often to the claim that 3D gravity is somehow related or equivalent or whatever you want to say to SL2R times SL2R Chern-Simons theory. So there are many, many problems with this kind of type of relation. So I'll just mention a few for the experts. So one is that the global structure of the gauge group is not at all clear. I think the best one is still PSL2R times PSL2R, but also that has problems. There's a problem that the dry band needs to be invertible, whereas in gauge theory, there's no principle that tells you that this kind of combination of gauge fields needs to be invertible. There's a mapping class group action in gravity, but there's no mapping class group action in Chern-Simons theory. In gravity, we sum over different topologies. We don't sum over different topologies in Chern-Simons theory, and perhaps there are more.
There's a mapping class group action, you just don't mod out by it.
Yeah, so in gravity, we mod out by the mapping class group action, and gauge theory, we don't. If you don't know what that is, don't worry about it. Okay, so chirogravity is the simple theory where you, instead of taking 2 copies of PSL2R, you just take 1 copy of PSL2R. And you consider this as a toy model for 3D gravity, and you keep in mind all the things that I've said that are bad about this correspondence. So in terms of holography, such a theory of gravity would be a theory of gravity that only involves, say, left movers and doesn't have any right movers.
So is this some 3D analog of self-fuel here? You take this plus.
Maybe morally, yes, but
Yeah, more.
morally, yes. So it reduces the degrees of freedom by half. So I guess, but yes, but of course we can't have self-duality in 3 dimensions.
Yeah. But like we find some kind of integrability, or like, okay, you'll talk about this.
Yeah, so this theory is a little bit better. So one feature is that for chirogravity, there's a quantization on the ADS length. So to get a consistent theory that's just in Chern-Simons theory, usually the level is quantized. And so this argument tells you also that the ADS length has to be quantized, and it's quantized exactly. No, it's also for the number. So the relevant thing is, so yeah, we can discuss it, but it's also for PSL2R. For U1 Chern-Simons, for example, is also, okay, that's also compact. But PSL2R contracts to U1, so the quantization condition is the same as in U1 Chern-Simons theory. So the relevant thing is if you compute an integral over a 4-dimensional manifold with some SL2R bundle over it, and you compute trace f which f over that manifold, if you can get a non-trivial number, non-trivial for second Chern class, then you need to have a quantization.
On manifolds that are covariant to
the 4-dimensional manifolds don't need to be
this
covariant.
argument does apply to the.
So it doesn't. So for the non-carrier version, you would just find that the difference. So you could in principle have 2 different coupling constants. The difference needs to be integer, but the sum can be anything. So this is for PSL2R. If you would do the Chern-Simons theory based on the universal cover of SL2R, then you don't see this quantization condition. Yeah, but you should expect such a quantization condition because you know that chiral CFTs are only consistent with this when the center charge is a multiple of 24. Otherwise, there's a gravitational anomaly in the boundary. So that makes sense that there is some condition like that. I can tell you later how to precisely see it if you want. But so the nice thing about this theory, it's maybe a little bit strange, but it has a much nicer phase space for the purposes of quantization. And the phase space is now, like Dan was asking before, it's just the moduli space of Riemann surfaces without the cotangent bundle. Because basically we halved our degrees of freedoms, and after we did this, we essentially this amounts to throwing away the cotangent directions. And the symplectic form now is given by the Peters symplectic form. But again, there's some amount of choice in this.
And this space now be seen as O2 functions and moduli space. It's a geometric structure involving your gauge field A.
So the phase space you can see as the moduli space of flat PSL2R bundles over your surface. And strictly speaking, it's only component. Yeah, there's again these mapping class groups and global issues, but after that, it's so for the gauge theory would have given you a tight mirror space instead of moduli space, for example. So the main thing why I want to consider this theory is because it has a compact phase space. And every unit volume of a phase space roughly gives rise to one quantum state. And so we expect that the dimension of Hilbert space is now finite dimensional. And every partition function we can compute is now finite dimension, is now finite. And in particular, we can now ask what is the partition function of this theory on manifolds of the same form. And almost none of those, as we discussed, admits saddle solutions of the equation of motion. And so now I show you tell you roughly what the result is. And it's very strange if you think from the gravitational path. So first order approximation, meaning for a very large central charge. Large central charge roughly means small h bar in this quantization. So if you're small h bar, then you have many quantum states. And it's a good approximation to just say the number of quantum states is the volume of your phase space with the correct normalization. So this is the normalization. This is the dimension of phase space. Here, sigma is again a compact surface, first for simplicity. And then you get in the volume of modular space. And with the normal volume measure that we're using, this is the bipartition volume, which is very well studied in math literature. If you go to very large genus, the thing I want you to notice is that it's known what the asymptotics of this volume are. So there's this, I'm throwing away all kind of irrelevant factors here. So the relevant factor here is that this goes like C over 3G minus 3. You should think that C is like 1 million or something. And then there's a factor, how this bipartition volume diverges, which goes like 2G factorial. So it diverges very rapidly. And now to compute the full gravity partition function, what we should do is to sum over all the three-dimensional Bloch manifolds with given correct boundaries. So this is the case here without any boundary, but it's relatively simple to also include boundary. And in particular, this includes these manifolds that we're discussing here, but also other manifolds, like, for example, circle bundles over Riemann surfaces, or you could imagine much more complicated things. But already you see, if you try to sum only over those manifolds, you already get a very badly divergent result. So this gives this 2G factorial divergence, and it gives it with a very large coupling constant in front. So sometimes we're facing these kind of situations in physics. For example, if we do something like Feynman integrals for gauge theory, then they're also diverging in a similar way. There's a small coupling constant in front, and we know how to make sense of it non-perturbatively by including some kind of instant constants. But here we have a large coupling constant, so this perturbation series immediately breaks down. Okay, so that's very bad. I'll also tell you what happens if you actually only look at fixed topology, but you do it exactly in C. So you can quantize it exactly, it's not so difficult. And the answer in this case is you can use a technique called geometric quantization. And the Hilbert space now turns out to be the space of holomorphic sections on some certain holomorphic line bundle over boundary space. So as before, we have to roughly separate into positions and momenta and declare that our wave function only depends on some positions. And here you should think of the positions as being Z and the momenta as being Z bar, roughly speaking, because this is a complex, it's actually Kähler space, this modular space. And so if you say that your wave function depends holomorphically on Z, the correct way of saying this is that it's a section of some line bundle over modular space. And maybe some of you know at genus 1, this is a very famous object because it just says that the Hilbert space consists of modular forms of weight C over 24. And here I have the formula for you how big the space of modular forms is at various central charges. So first of all, central charge again has to be a multiple of 24. So the C over 24 is always an integer. And then depending if C over 24 is odd, there's no modular form. If C over 24 is even, then there are some modular forms. And there's some kind of weird case distinction depending on the mod 12 properties of C over 24. So, and this is a very strange and erratic function of C. If we would have computed something like this from a semi-classical gravity perspective, we would have guessed that there's some nice smooth answer. Maybe it's not a very nice answer, but you would still have thought that there's like a 1 over C expansion or something like this. And so mathematically, you can trace this kind of weird behavior to the fact that the phase space is actually an orbifold and not a manifold. If you would quantize on a manifold, you usually don't get this kind of strange behaviors. On a manifold, for example, if you just consider genus 0, then the phase space is actually a manifold. And when you have a manifold, then there are these kind of index theorems that compute you the number of sections on these line bundles. So there are some characteristic classes here that you don't need to know about. But one last thing I want to mention is that there's a very nice technique, it's called topological recursion, that computes these types of integrals over modular space. And roughly speaking, the idea of topological recursion in a picture is like this. If you want to compute an integral over the space of surfaces with some given number of boundaries and some number of genera, then you can split up the computation and some sum over different contributions. There's one type of contribution where you split up the surface into two parts that are connected by some kind of long tube. And there are some contributions where you keep only one part, but there's kind of tubes. So this would do another hole here. And there are some recursion relations that compute you these partition functions recursively in a number of boundaries and genera. So this topological recursion is essentially equivalent to random matrix models. And you can more or less go back and forth. And this computation essentially shows that there's still a random matrix model dual in some sense to this chiral version of 3D gravity, but it only captures the manifolds of the form Riemann surface type circle. So I think it is a version of holography for 3D gravity, but it's more like 2.5 dimensional gravity because there's like a Riemann surface, but then you fix the third dimension to be a circle. So it's not really 3-dimensional because you're not allowing the circle to do whatever it wants to do. But what is nice is that this is a deformation of a more well-known story from JT gravity. So there's a particular limit you can take and you go back to JT gravity. That's the model that has been studied a lot recently. And that makes sense because JT gravity is the dimensional reduction of a 3D theory of gravity. So if you reduce, then you go back to JT gravity. But here you can take the circle big and you get some non-trivial deformation.
You could say that Q deformation.
It's not a Q deformation. Yes.
Can this, I guess the earlier version of what from formal gauge fixing and filter definition where you could write it just as a function of the verify. Does this thing you're calling chiral gravity, can you write it as a function of the measure verify?
I don't think that you can. No, so you're taking the dry bind and spin connection, you're throwing out some of the components.
So why is this gravity? It's not a theoretical method.
Yeah, if you want, you can say it's not gravity, but it has all the same features, I think. So you're just taking the first form, you're just taking solutions of 3D gravity and you're forgetting about some components essentially. But it still has all the features like mapping class groups and invertibility of dry bind, and these kind of features are still there. So yeah, we can discuss whether you should call it gravity or not. It's just some stupid toy model that I cooked up. That
So you probably know there is another theory that
of chiral.
also is chiral.
Yes, and it's different than this one.
This construction doesn't work for that.
Yeah, so the other one that you probably have in mind is the one where you add a gravitational Chern-Simons term.
Yeah.
That's not this one.
But does this construction work for that or not?
I don't think so because you still have massive modes in that theory, right? It's
No.
no. But
No, it's chiral. There's no massive.
so yeah, but the equations of motion are different than for this one. So I can't really. I don't know what the phase space, for example, would be for them. And I thought there's like many papers. Probably
So you did
that.
Okay. You don't know.
I don't know. I know that these other theories exist and that they don't exactly fall in this framework, but maybe you can address them.
So the 3D gravity theories you said aren't going to work because there are these divergences when you have this.
Yeah, at least I don't know how to make
And,
sense.
and so now you're looking for analog, something analogous to them that might work.
Yeah, it's simpler, but there are still many things that don't, like even if it works that you have finite partition function for a given topology, then you still have either some of topologies and that gives you badly divergent. So I think all of these arguments eventually, I mean, I tried to understand 3D gravity better, but like the story only convinced me that it doesn't work very well. So there are many problems that part of them are very well known, but I think, for example, this like these infinities are not very well appreciated in the literature. I guess people are continuing to make sense of it, and maybe there will be some sense at some point. But I think these kind of problems are very serious, and I don't know.
If you thought of it as a gauge theory and you summed over all topologies, you wouldn't be surprised if you got divergence.
No, yeah, I wouldn't, because I would sum over topologies by hand, And there's no principle in gauge theory that tells me to sum over topologies. So, yeah. But even in gauge theory, you would find this kind of divergences because it's gauge theories with non-compact gauge groups. Usually we're considering something like SUN or something, but here it's SA2R. So even for SA2R Chern-Simons or something, the partition function on like a Riemann surface times circle is also infinite because the Hilbert space is infinite dimension. Right. I think that's essentially it. So I'm going to my conclusions, and let me just reiterate some of the kind of bad things that we found. So there are many theoretical obstructions. If you want something like a pure theory of gravity, which many people want, and in particular, and also if you want to understand the gravitational path integral more precisely, then you have to face these kind of issues at some point. So we thought that there are divergences even if you fix your topology. But there are also divergences if you sum over topologies, even if you made your topology for every fixed topology, you somehow got a finite answer. And then the question I didn't address at all here in this talk is which kind of geometries you should even include. So we could also discuss, we could put some kind of conical defects in our surfaces. We could cook up all kind of stuff and try to see what we get. But yeah. So yeah, I told you that some of those issues can be addressed in low dimensions. So we know kind of well what happens in 2 dimensions. In 3 dimensions, we already know very little. In 4 dimensions, we know exactly 0, I think. So it's very unclear whether these troubles can be overcome and whether there's something like a pure theory of gravity. I tend to think there's none, but I'm very happy to be convinced of the other opinion. And so this raises the question whether string theory is perhaps the only answer to quantum gravity, and maybe we make progress in the next couple of years to try to constrain quantum gravity calculations and see that string theory is really the only answer you can get. So since I'm German, I thought I need to include a German quote in the end. So there's this famous Latin saying that we don't know and we will never know. But there's a very famous retort of David Hilbert, and he said when he retired that we must know and we shall know. And it's actually inscribed on his grave. You can see it in Göttingen. And with that, I hope that we can make progress in the next couple of years. Thank you.
That's a question.
Yeah, sure.
I know we're a little bit late here. So it turns out this is the black hole initiative.
Yes.
And so we're interested in black holes. You know, I heard you mention black holes earlier in the talk.
Yeah.
That these topologies admit, or this theory admits black
Mhm.
holes. So, and you're trying to find ways of simplifying the problem.
Yeah.
So, and I'm an astronomer, so I know black holes. I'm pretty sure they exist. You know, and so let's take that as a given. But if you spin a black hole, then you get symmetries. And it's, in particular, if you go to A=1, for example, then you get certain symmetries that may simplify things.
Yes.
Is that also something that you can explore here, or how do you tie this to black holes?
So yes, you definitely can. People have done a lot about this in 3D gravity. So spinning black holes.
I'm talking about extreme black holes.
Yes, exactly. So in this kind of sum over geometries. So I told you how to compute partition functions on this. So in principle, you're trying to compute partition function in ADS, and there are some kind of extreme black holes sitting in ADS. So these correspond to some flipped versions of this solid donut. They're flipped in some kind of extreme way. There's some kind of notion that you can go close to extremality, and actually that's where the troubles arise in this kind of sum over.
So that's a problem. That's not a solution.
Yeah, they're just problems. They're very little solutions.
I thought it would make it better, you know.
Yes, so you can control it better because there's, for example, if you go near extremal, then this chirogravity is actually probably a better approximation because near extremal is sort of ground state with respect to say left movers but not right movers. So you can only excite like one direction, and then the chirogravity is probably given a better description. In fact, there has been lots of work that if you're in the near extremal limit, then 3D gravity reduces to 2D gravity in a sense, and the coupling constant becomes small. So you can actually control 3D gravity better in this regime. And so one of the potential solutions to the problem that like the sum of a topology is very ill-defined is to use the 2D, what we understand in 2D and uplift it to 3D. So that's Maxfield and Turiashi's work from like 3 years ago. They show that some of the problems in 3D, some of the topologies can be overcome using that. So it's definitely true that near extreme is better controlled than like just arbitrary black holes. But still, I think they're
I will.
Yeah. I mean, one of the things that he did when he threw out that other term was to refer to a theory in which the only consequence was behavior.
yeah.
And that's, things became simpler when he did that for exactly the same reason it becomes simpler for the extreme. It's the same truth.
Is there, again, maybe this is a naive question, but is there also a simplification that might occur if you only try to find a gravity that held very close to the photon orbit? If you limited its geometrical range of applicability?
So it's supposed to hold inside the photon or outside the photon orbit?
Just like at the photon.
Sorry, I don't know. Well, at the photon orbit, its gravity is supposed to hold and outside not.
Well, like if you could perturb around the photon orbit, does it help to make it so that you only need to observe something at close to the photon orbit, not at it, but close to it?
Yeah, it's very hard here to do something like that. Because like, so the problem is in all these kind of, so this kind of approach where you just do the path integral or canonical quantization. So you have to ask what are the things that are well defined to observe. And it's very hard to insert something like a photon orbit because you can act by diffeomorphism and shift the location. It's very hard to define some kind of operator where the photon orbit is. Maybe that's possible, but that's just like it's a difficult thing.
There isn't even a photon orbit for the beat to do.
Oh, there is not. Okay.
Oh,
I see. Okay.
okay. Good question. That's eventually work.
But you can imagine doing this for like a 4D setting or something.
But even in 3D.
Yeah, we should probably lock it up. So let's thank our speaker again.